confusing for my head. Okay, here. Yeah, so I thought I would do something a bit different and talk about a way to use things we have learned over the past few years on predicting statistics of redshift space distortion in galaxies to apply to a new observable. Um, and I want to mostly do it on a blackboard, but I have a few slides to show on there, and a glass of water because of Sweet Caroline or something that happened later. So what are peculiar velocities? So normally in redshift space, normally in galaxy surveys, what we do is we measure galaxy redshift, right? So it's, schematically, I should have tried this. Schematically, what we do is we measure some cosmology, some redshift of a galaxy based on some line, and we can roughly split this into some cosmological piece and a piece that is due to the peculiar velocity of the galaxy. And roughly speaking, you can think of the peculiar velocity as just this piece of the redshift as just being the peculiar velocity of the galaxy divided by c. And at low redshifts, there's something we can do, which is that we can actually measure the distance, and therefore this cosmological part of the redshift using a completely different way than just the redshift of the object. So for example, in DESI, people are going to use what's called the fundamental plane of galaxies, or the Tully-Fisher relation, both of which allow you to infer basically either the brightness or the size of a galaxy, and from that you can infer the distance based on the angle or the inferred brightness. Or for supernovae, of course, we know that we can directly infer the magnitude of these things, and from that infer the luminosity distance. And both of these allow us to probe basically allow us to disentangle the cosmological redshift and the peculiar velocity. And did I? No, I did not. So one thing you may be wondering is, well, why is this useful? Because haven't isn't it true that all these distances are very poorly measured, right? Isn't it true that these distances, we're already arguing about all these possible errors on all these things. How can it be that this is even a useful measure? And the reason is because we basically live in a regime for these peculiar velocities that the noise becomes super subdominant to the signal at very large scales, right? So it's kind of different from galaxies where you're always having some shot noise. In this case, if you measure a peculiar velocity on large scales, even if it's very noise dominated, you're really kind of directly measuring the large scale flows on the universe. And so I kind of got interested in this topic because we have all this data coming online from DESI, from LSST in terms of supernovae, but there really hadn't been very much in terms of predictions for what these statistics will look like. So what mostly people have done, unlike say galaxy clustering or even weak lensing, is people have just used linear theory times some function. Of course, as I'll mention, some people in this room have previously contributed to this area, but the upshot is that even on scales of say 0.1 megaparsecs, 0.1 per megaparsecs, we're really measuring the very low redshift universe, so these scales become very nonlinear. And so the state of the art that people have done, as I'm showing here, is that compute a covariance between the different velocities, between different redshift, between different line of sight directions and angular directions. They assume some covariance that comes from linear theory. That's the state of the art at present. And so I was really just trying to understand, can we do a bit better? Okay, no. And the answer is yes. Okay, so why is that? So let me begin just by describing what peculiar velocities are, right? So normally we measure a galaxy, suppose I can disentangle this thing. Now normally I measure some density field of galaxies, which I'm going to call rho, as being just 1 plus the overdensity of galaxies. So here I'm assumed that I've already removed the overall the overall average number density. Now, if I measure a galaxy velocity field, then I can form some object that looks like that I'm going to call rho L, which is basically this times the galaxy velocity to some power. Now, it's important to note that here I will always refer to just the line of sight component of velocities, because from this relation, all I know is how fast the galaxies are moving away from me. In this sense, I almost never have a way to measure the velocity of galaxies in the transverse direction. So in particular, I'm defining this object U to be the velocity of the galaxy times the line of sight divided by the conformal Hubble rate. So what can I measure, right? Once I have this thing, what can I measure? Essentially, the most obvious thing I can think of measuring is basically some power spectrum of this guy, right? So I can measure what I'm going to call PLL prime, which is just the power spectrum of the peculiar velocity taken to some power L and to some other, and its cross spectrum with the field multiplied to some other L prime. Yeah, so in the literature, I mean, this is more or less what people always want to measure. And in this talk, I will in particular want to focus on kind of a very specific combination of these PLL primes that are the peculiar velocities, that are the pairwise velocities. And by this, I mean that I want to measure the following object. I want to measure this correlation function of n, which is equal to the correlation function of galaxies weighted by their pairwise velocity. So here, what I mean is that I have the density of galaxies measured at some position, x, at some position x1, the density of galaxies at some other position x2, but I'm going to weight them by the difference in their velocities at this point. So I can measure u1 and u2 for them separately, and I want to take this combination u1 times u2 to the n, where u1 is the galaxy is the velocity evaluated at x1, and u2 is the velocity evaluated at x2. So why would I look at this object as compared to the more general class of objects here? There's one very nice property is that I can suppose that there is some bulk flow between these two objects, right? Some very long wavelength motion. Then in this combination, these bulk flows will cancel. Now this is not completely true because in the real world, I'm looking at velocities at different angles, and so if I have some flow in this direction and some flow in this direction, taking their difference will not necessarily cancel. But this is true. At least this kind of Galilean invariance of this statistic is at least true in the limit of small angles. But there actually is a deeper reason for this. And of course, okay, sorry. Let me say that. Of course, measuring this is basically just a subselection of measuring these guys, because of course I can expand u1 to some power and u2 to some power, and I would cover a linear combination of these guys. So for example, where did I put? So for example, I can think of the first moment really as just 2 times the p of 0, 1, because all I'm doing is taking one velocity if I have this. But okay. So why is it that I want this to be, why is it that for a deeper theoretical reason I want to measure this, and I'm going to try to convince you now that it's because this object is just exactly what we have learned to predict from theories of redshift space distortions for galaxy surveys in say the past 10 years. From some people aren't in the room, but Misha, for example, has done a lot of work to predict these things. So let's begin from the beginning, right? So what is the RSD mapping? The RSD mapping is basically that we observe some position I'm going to call x, and this position is equal to the real space position plus the velocity u, right? So this is basically the starting point for all redshift distortions, which Gigi was telling us yesterday as being one of the probes that future surveys are targeting, or current surveys are targeting. And how can I use this relation? Well, if I have this, basically tells me that the galaxy density field that I'm observing at position S is equal to the following. Is equal to, if I integrate over all possible positions that could have entered. How do I put this? Yeah, if I integrate over all possible positions that galaxies could have been in real space and computed which ones after this redshift space mapping will arrive at the real one, it's the galaxy density in real space times a Dirac delta function, which is equal to S minus X minus U evaluated at X. So basically, this is a way to enforce number conservation between galaxies in real space and redshift space. And now this allows me to do something very nice. So now, if I take the Fourier transform of this guy, this basically tells me that the redshift space Fourier transform of the object is equal to, again, this integral times 1 plus delta g of x times e to the I kx plus u. So basically, in doing this mapping, what I've done is I've given an extra phase proportional to the velocity to the galaxy field itself. I'm taking normal Fourier transform times this. And starting from this, how do I? And starting from, and starting from this, what I have is that, for example, the power spectrum, if I take the 2-point function of this guy in redshift space, what I can get is that the two-point function is really equal to the following. Where I have defined this delta u, this guy delta u, to be this pairwise velocity that I just written down. So now you immediately see that the redshift space power spectrum of objects is really given by something that is very related to the statistics of this pairwise velocity. And in particular, this is almost kind of a silly formula, but in particular, if I now expand this object and I say that I want to define, if I really want to count the powers of velocity, I can define this object with kind of a counting parameter lambda in front of each velocity. Then I see actually that this object that I've defined above, the endpoint statistics of the pairwise velocity is really nothing more than the derivative of this guy, right? Because each derivative of lambda and the counting parameter of velocity that I take, each derivative just gives me one of the powers, right? Each time I take a lambda derivative, I bring it down. And so this is really nothing more than dividing out the line of sight component of the wave vector. It's really nothing more than taking this guy to some derivative. So this formula was derived by Noanori Sugiyama and some others almost 10 years ago now. But what it really tells us is that if I have a model for the redshift space power spectrum, which every single galaxy survey now has as kind of an official model after a lot of work by people in this room, then I immediately also get, as a consequence, a model for the measurements of the peculiar velocities, right? As in, the model of this thing immediately implies what the model of this thing is, and there's no additional freedom in that. And so, what I want to do for the rest of this talk is basically try to see how can we take this formula and work it out, and work out all the consequences. Let me make some comments. So one comment I should say is that there's a reverse of this, which is that if I have a model for the peculiar velocities, I can of course work backwards to figure out what the redshift space power spectrum is. So this is this approach known as the distribution function formalism that Urosh and Pat McDonald worked out again quite a while ago now. But basically, if I have this thing, I can sum them back up to the redshift space power spectrum, and that's actually, I think, quite a powerful approach to understand redshift space distortions. But of course, I can also do the following. So here, I'm always assuming that there are peculiar velocities by setting this counting parameter 1. I can also evaluate this derivative when the counting parameter is 0, and that will give me things without redshift space distortions. And of course, all these things are linked, so there's really one happy family of all these different approaches to understanding the large-scale structure. So let me just really give kind of two main consequences. So I really just want to talk about kind of two main consequences of this formula. So the first is, we've been talking for the past, we've been spending a bit of time talking about projection effects and how many parameters there are in the EFT. So I want to show this as an example of something where the EFT actually doesn't give you any new free parameters, and this is kind of a way to break the degeneracies inherent in these models. So because any model of the power spectrum, say of the two-point function for galaxies, is implicitly a model for this, I don't need any new parameters. So let me start with the simplest example, which is linear theory, right? So in the linear theory of galaxies, I have the following. I have that the power spectrum of galaxies is given by this formula that Kaiser developed in the 80s. It's just the power spectrum for galaxies is just equal to B plus F mu squared times the power spectrum of matter. This is the so-called Kaiser formula. So what does this mean? This means that I can use already this formula to derive what the linear theory of peculiar velocities is. For example, if I take this derivative, then I show that basically, let me not write this like this. That, for example, the first pairwise velocity moment is just equal to 1 over ik mu of dd lambda of this guy above, and you see that this is equal to 2 minus 2I times f mu squared divided by k times b plus f mu squared times p of k. Right, so just an example, and we can proceed, of course, to see that there are only really two leading order pairwise velocity moments. The first one and the second one, which is just equal to 2f squared mu to the fourth over k squared p of k. These are only two ones. But you immediately see that in order, of course, it's kind of a simple example, but you immediately see that there are no new parameters that I need to introduce into the model. There's a direct prediction already for what the peculiar velocities are, already given the clustering model of the galaxy. Now, how can I take this further? Well, I can take this further. By the way, please stop me if there are any questions, comments, etc. So the way I can take this further is the following. One of the things that people are concerned about is in many of these surveys that there are many so-called EFT parameters. And one that you will hear about a lot are so-called counterterms. So in the galaxy power spectrum, we have a lot of terms that look like k squared times p of k, right? There are a lot of contributions that we call counterterms that look like k squared times p of k. And in redshift space, there are quite a few of them. So in redshift space, the form that they typically take is b plus f mu squared times a term that is a constant plus a term that is proportional to mu squared plus a term that looks like mu to the 4. So in DESI, for example, I mean, this is kind of this. I mean, basically in all analysis of one loop power spectrum, this is what people do. And now you have these three parameters, which I'm intentionally not writing down first. In redshift, when I take into account the velocity counting, what I get, just to make sure I write this down correctly. Yes. What I get instead is that there's one term that's isotropic that doesn't depend on the galaxy velocities at all. There are now two terms. There's one term that depends linearly on a velocity, and one term that depends quadratically. And then there's a term that depends quadratically on the quadratic on the velocity, plus a term that depends cubically. And there was some debate over this in the literature early on in the galaxy power spectrum, but this is basically what it is. And what you see is now, if I take into account the velocity power spectrum, I have basically 5 free parameters as counterterms. And again, if I only measure the galaxy power spectrum, I cannot distinguish between these parameters, but essentially I have to fit them all. But now the nice thing is that each of these terms has a different lambda dependence, right? So each of these terms has a different dependence on the velocity. So when I measure the velocity power spectrum, I can determine them each separately, right? So remember, at linear order, I have basically a mu squared component of the first moment, a mu to the fourth, and then of course I have a mu to the fourth here. And so what I can really do is try to use this kind of polynomial dependence of the galaxy power spectrum to kind of disentangle these. And indeed, there's something even more interesting, I think, which is that people have been talking, for example, in Euclid about, or in DESI as well, about using these so-called VDG models. There are ways to resum the galaxy velocities. And these models will have very, very specific implications for what peculiar velocities are. So in the simplest case, I can think of, for example, in the simplest case, for example, I can think of the following kind of term, which is not nominally existing at this order in perturbation theory, but which Misha showed, for example, some years ago was large, which is something that looks like k to the 4 times mu to the 4 times the power spectrum times. So now I can ask the following question: is this, are there terms that are enhanced by large velocities at scales? And it turns out the answer is yes, right? It turns out that if I go beyond the spirit of perturbation theory and add, of normal perturbation theory and add in terms that I know will be large, I can try to see if adding in terms like this, I can try to see if adding in terms like this will help my expansion into peculiar velocities. And it turns out the answer is yes. So I think one kind of very powerful way is to then go further and ask, well, if I use more advanced forms that people have proposed, like the VDG model, will it still, will it still be a way, will it still yield a model that will probe the peculiar velocity as well? I think that's kind of a fruitful way to look at it. But before I go any further, I just want to show that this model actually works, right? So yeah, so here's some fits to halo power spectra in simulations. So I'm showing here. I have this. I'm showing here on the left. On the leftmost plot, this is just the normal galaxy power spectrum that we fit in all surveys like DESI and Euclid and so on, and BOSS. But here, for the same exact galaxies and for the same velocities that have produced these redshift space distortions, I have now measured the dipole and the octopole of the first moment of velocities and the monopole and quadrupole of the second order velocity. So you can see where these surveys will be most powerful is at very low redshifts, and I've shown not so terribly important for this talk predictions from kind of the Eulerian and Lagrangian EFT-Zariski structure, and they're broadly able to fit. They're broadly able to fit velocity, peculiar velocity statistics up to some scale. That's about 0.1. I mean, it's significantly less than we go to at higher redshifts, which is about 0.2. But you can see that we're able to kind of qualitatively at least describe these. And the important thing again is that I'm not using any new theory developments, right? All I'm doing is taking the implications of this thing, taking the derivatives of our predictions for the galaxy power spectrum, and yielding these predictions. And you can see that for these even for these very large volume simulations that are much larger than any peculiar velocity survey we can have, I get much I can really match to what these peculiar velocity statistics look like. Yes. I fit everything simultaneously. Yeah. Yeah. So exactly. Yeah, that's a good point. So in fact, I mean, if I were to have fit the same EFT models with just this guy, I could have gone a better range of fit than I get here, right? So you can see that there is some cost to fitting them all simultaneously, but that nonetheless the model is able to fit them all together. Yeah. Yeah. So this is the good. So the reason for this is because of discreteness effects. So if you basically, because I'm measuring like the octopole of this thing, it's much more sensitive to the discrete K modes, and they're much larger than you would naively expect for like the power spectrum where they're small. But this is also why I mean you can see also in the quadrupole we usually have this problem where if you see the scatter, it's much bigger than the naive statistical error bars. But if you compute the window function, you will see that they will just match exactly. Yeah, thanks for asking that, Dex. So okay, I'll show that. So I want to talk now about a second kind of more academic, but I thought kind of for this audience maybe interesting consequence of this formula. So by now most of you have probably heard of this issue of the BAO, right? So we measure the BAO, and we know that nonlinear structure formation kind of damps the BAO, kind of reduces the signal, and kind of the easiest, the lowest order for what that does to the BAO is it introduces an exponential damping, or a Gaussian damping more accurately. That is to say, if I separate the linear power spectrum of galaxies into a wiggle, so I have the normal formula that I was just showing of the Kaiser formula for redshift space distortions. But now if I look at just the linear power spectrum, I have a piece that's not wiggly. So I have the BAO, and the BAO has some broadband power and some wiggly power. Basically, what this does is it takes the wiggly component of the power spectrum and damps it according to e to the minus k squared sigma squared mu, where this sigma squared mu is a reflection of large-scale bulk motions of galaxies. So this all seems very nice and simple, and in fact, people have shown that this is this basically captures most of the effects of what the BAO looks like in galaxies. But it has kind of a very interesting consequence in terms of peculiar velocities, because part of the bulk motions that remove the BAO signal in galaxies is actually due to long wave velocities. And so what this means is that this sigma squared mu has a part that's isotropic, but has a part that's directly proportional to the velocities. And I won't derive exactly why, but there's an angular component to this damping that is proportional to the linear growth rate of galaxies. And now what does this mean? This means that when I take this derivative, I no longer recover just an exponential damping of the BAO, but I get something much more interesting, right? So if I basically what I'm trying to say is that if I where do I write this? If I take this derivative p, for example, the first moment will be equal to a piece that has just a purely exponential damping. But then there will be a second piece that's proportional to d sigma squared d lambda, right? Which again has this dependence on the velocities times 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 something, right? So before I go any further, and to ask, let's just see whether it actually happens, right? So I took slides, a kind of a very simple example. Uh, I took in these slides as an example a universe where all the displacements of galaxies just come from their linear motions, right? Basically all of structural information just comes from galaxies moving ballistically in one direction. This is the so-called Zeldovich approximation, and in this approximation we can compute exactly what exactly the statistics to all orders in perturbation theory. And so that line, the exact thing, is given the black dashed line. And you can see what linear theory looks like without any of this damping is for the peculiar velocities is just this blue line. And so what you can see in this universe, the BAO are not only not in accordance with linear theory, they actually are of the complete opposite sign. Even at very, very large scales, even at scales, basically even in the leftmost corner of this plot. And if you look carefully, what you can see as well is that the BAO goes to 0 at several points at several points in this plot where there's a huge, where there's a peak. And so why is this? And the reason is really just directly explainable by this derivative formula. Right here, I have this term times that's equal to k squared sigma squared. So now instead of just having an exponential damping, I have a term that's proportional to a polynomial times an exponential damping. And this produces kind of a very, very interesting result for the thing, for peculiar velocities. And I mean, really, what this is saying is that in the case of galaxies, we have to do this exponential resummation because this damping of the BAO is much larger than the other nonlinears of the problem. And in the case of peculiar velocities, I have to go beyond this exponential resummation because there are other large contributions to the statistics of these peculiar velocities that are not simply removed by resumming them into this exponential. Yes. Where's the k dependence? Yes. So the k dependence is just not, is in front, so it's k squared times an. Oh, sorry. This is a k. Yeah. Sorry, this is a k. Wow. This is more to do with the large scale bulk motions. The fingers of God will also do something similar, but they're kind of a more perturbatively treatable effect than this. So these are due to very long wavelength motions of galaxies. Kind of you can think of it as being the mean dispersion of galaxies on the scale of the BAO, or the mean relative motion, like how far galaxies that start near the BAO will move apart or closer. The fingers of God, in fact, would be here. The fingers of God would be absorbed into these terms I was talking about earlier, these kind of counter terms. Yeah, but in fact, you'll see, yeah, as you're pointing out, I think these terms also modify the shape of the BAO. It's just kind of a, it's just that these ones are kind of curious because they're they're kind of linear modes. Actually, they're not due to the small scale motions of galaxies. They're really due to the linear motions of galaxies. So let's see, what time do I have? So I want to maybe just give a sketch as to why this is not surprising. There's a little sketch. Yes, I really want to give a little sketch for why it's not surprising, and kind of to explain also your question as to why, how I perhaps could have derived this starting from the beginning. So the way we understand these BAO is that galaxies, have some trajectory through space-time, so that their current positions in space that we observe are equal to their initial positions plus some displacement that is a trajectory in time that I'm calling psi here. And of course, because I'm observing them in redshift space, I'm not even really observing that. I'm adding their initial position plus this displacement plus their velocity, which is the derivative of the displacement. And I guess I erased it, but from the same logic that we applied to get the redshift space partial derivative before, I can do the exact same thing, and I can write that now. I can write the power spectrum of galaxies through number conservation as being an integral over the initial positions now, and an average value that depends on sorry, I'll explain what this means in a second. On their densities weighted at their initial positions, times this phase that is proportional to the pairwise motion between galaxies. So this delta S that I've written now is equal to the trajectory of galaxies at one position minus the displacement of galaxies at a second position. And why is this formula useful? Well, this formula is useful because I can try to, oh my gosh. This formula is useful because I can try to find contributions to this kind of expectation value that only depend on the large scale motions of galaxies. And the reason, right, so essentially I want to look at, sorry, 1 second. I want to look at contributions to this power spectrum that only depend on the Gaussian moments of this. So I want to look at essentially parts of the power spectrum that look like, okay, this integral again, that's a bit annoying, over the things that look like just the statistics of this one guy, which are the velocities themselves, times the rest. So now this guy, we know has a BAO feature, right? So the key point is that this guy has a BAO feature. So it has something that's very, very peak at the BAO at the BAO scale. And so what this kind of term can do is basically pick out what the average dispersion of the galaxies are at the BAO scale. And if I evaluate this for a Gaussian field, I just get that the exponential of the Gaussian field is given just by e to the minus 1/2 k squared sigma squared of the field times the BAO feature. So that's how I got this. That's kind of the simple way you can think about the damping of the BAO peak. But now in the peculiar velocities, I have a slightly different picture, right? The slightly different picture arises because now I'm not just interested in an exponential of the velocities. I have a term instead that, right? Instead, I can think, for example, in the first moment, I can think I'm essentially doing this expectation value. Right, so now I have a thing that's multiplying this whole thing that's also proportional to the velocities. And so what this means is I can't simply look at the expectation value of the exponential. I really have to look at the expectation value of the exponential times some power of the thing in the exponent, right? Right. So of course, what this means is that two kinds of contributions to the power spectrum can be large. The first is something that looks, of course, as we look at it, I separate out the exponential times the galaxy density times the velocity. So this is the kind of term that would give you the exponential damping. But then I can also have a term that looks like the velocity times the exponential and then times the galaxy densities. So spiritually, what this suggests is that the power spectrum of the galaxy, the power spectrum of velocities, has a term that looks like a damped, simply a damped wiggly part of the velocity, but it also has a polynomial piece that looks roughly like k times sigma times the power spectrum. Right. So what's kind of nice about this picture is that the BAO and the velocities is kind of a mixture of what you would naively expect would be part of the velocities and part of what you expect in the power spectrum. And again, because we have this formula that I've just now erased that links the power spectrum of the galaxies to the power spectrum of velocities, once I've made a prediction for the power spectrum, it basically it leads to kind of a completely determined resummation of these long wavelength modes for the galaxy. So all those are nice words, but the question is, does it actually work? So here I've shown from these simulations, basically pulling out the BAO wiggles for galaxies compared to what the theory predicts. And again, helpfully, and just to show that all the way work didn't go to waste, I'm showing what linear, this black dashed line here is now showing what linear theory would predict for the galaxies. And you can see that linear theory almost nowhere on any scale at any of these redshifts predicts what the BAO looks like. But if I just do the simple one loop perturbation theory trick and take a derivative, I can very precisely determine where the BAO looks like. Right? There's this excellent agreement between what this consistency relation between the velocities and the densities for galaxies tells you. Okay, I mean, to be completely fair, in order to make these plots, I had to remove the broadband shape of the galaxy. So there's there's a smooth polynomial that's fit through, which is shown here in orange. But most of the time, even this broadband shape is very fine. And what you should really notice is that these predictions of the theory that the BAO will go through zero at points that are on very large scales is completely is seen in the data very cleanly. And if I had instead shown the old predictions, frankly from some of my old papers of what the velocities would look like, you would see that the exponential only resummation of these velocities looks completely off. So in this case, for example, the exponential only resummation will look like this green curve, which even though it's less divergent than the unresummed version shown in blue, it still does not capture what the overall phase of the BAO is here. So it kind of works, and actually I think instead of going into more detail, what I'll instead say is that now what this sets up to do is to use the exact same kind of methodology that we have done for galaxy densities to make cosmological inference of peculiar velocity surveys. So just as a final slide, I wanted to show just a proof of concept, right? So what peculiar velocities really allow us to do is to measure the growth of structure in the low redshift universe very well. And so I just did kind of a simple example where I just want to measure the growth rate of galaxies. I want to measure the growth of structure through this growth rate f of z at low redshifts. And I've kind of constructed kind of a pathological example. So in this case, I'm allowing the counter terms to have essentially no priors. And as we've been discussing for the past several weeks, you would never really do this because we have some good theoretical intuition for how big these kind of corrections would be. But I just want to show here, I made this example here because, as we were discussing earlier, the peculiar velocity should really allow me to break all of these degeneracies. So if I measure just the dipole of the peculiar velocity in the first moment and the monopole and quadrupole in the second moment of the peculiar velocities, you can see that I can go from having essentially no constraint, or not 10%-ish constraint on the growth rate, to having really quite a tight one that improves by perhaps a factor of 5 because I'm breaking all these degeneracies into free parameters. Now, okay, you'll say, okay, in real data we'll have all kinds of additional error bars that are not reflected in the simulations. That's true, but at least in principle, what this is showing is that they can all be described by one simple kind of set of parameters. And I just want to emphasize that we cannot go to very small scales in this model because the low redshift universe is very nonlinear. But even then, on scale that we typically use these models, the peculiar velocity predictions for the EFT that just come again exactly from the same kind of models we've been using for the past 10 years, I guess past 5 years to study galaxy clustering, can predict, can constrain the growth rate to better than the 0.25% level for basically any redshift or halo samples we tried. So I think we're kind of in a regime where we can try to think about what kind of interesting science we can do by understanding very low redshift by understanding very low redshift peculiar velocities. Or do you? Yes. Yes. You mean here? Yes. Yeah. No, indeed, indeed, exactly. So that's right. So I guess I perhaps wasn't clear. So yeah, sorry. Let me write it here. I mean, I can think of the normal thing I mean, the normal thing that I'm resumming is just equal to uh, let's just call it x, right? Normally the thing I'm resumming is equal to e to the 1/2 lambda squared x squared, right? This is the normal thing in Zeldovich. And now you're asking me, now I have basically this, right? Now I want to take this kind of now I want to take, sorry, I don't know if you can see. Uh, now I'm taking the expectation value of an exponent times an x. No, no, indeed. So the sigma squared I wrote down here already includes the u in the exponential. So taking the derivative of it just brings down the part of the u that is not in the was in the exponential and producing an additional polynomial part. But no, it's still the large scale. It's still the large scale because it's just coming from exponential products. It's basically this argument here, right? Here, I mean, normally I can think of this guy as just resumming all the things that are the large scales, but you know, I mean, this is like delta to the n, right? So now I just want to basically make it delta to the n over 2, right? This is basically, I mean, the exponential comes from this, right? And now all I'm saying, all you have to do in this case is that there's a delta u times delta and also delta to the n over 2. So I mean, it's just resumming the same large scale things, but now you just have one additional diagram. So if you do the counting in this case, you can also show that you'll recover this formula. But it's entirely resumming the large scales. There's no small scales involved. That makes sense. Maybe I'm not explaining it very clearly. You see, I mean, so I mean, in this formula, right? So so in this formula, there's only large scales, right? The k squared sigma squared is purely coming from the resumming of large scale displacements. So if I take a derivative of it to get this new formula for the peculiar velocities, there's also no small scales involved, right? The only things that come out of the derivative are also the large scale modes. It's just a rearranging of the large scale modes to fit the Gauss peculiar to handle a case with velocities. That make sense? Yes. Yes. Uh-huh. No, no, no. Sorry. Yeah, I've not been very precise here in what I'm saying, but no. I mean, delta u in this case is just the velocity. It's the velocity of which I later resum only the long wavelength parts. I mean, this. I mean, yeah. So basically, I can separate this delta s guy into a delta s greater and a delta s less than, right? I can split them into long and short parts. And spiritually, what I'm doing is when I do this resummation, I only want the long I only want the long parts, right? But in all these formulas, yeah, I've implicitly assumed that sorry, I wasn't very clear, but in all these cases, I've implicitly assumed that I'm only resumming the long parts. Yes, yes, and then you perturbably compute the parts that are short because those parts can be expanded order by order in the EFT with no problems. Mm-mm-mm. No, okay, yeah. So the reason I wrote it like this was that there's a I mean, you have to iteratively remove the parts of the. So in other words, I mean, it's not necessary at linear order, which is where I wrote that equation down. But of course, as you point out, in this, I mean, in this exponential, there is a part that's already naturally taken care of at one loop. So really, what one means is what you're damping is the part that's not due to the long. I mean, this damping applies to the part that's not due that has all the long wavelength contributions subtracted, right? I mean, you have to compensate at each order, and when you do that, what you find is that so now I've done a separation of the power spectrum between the long and the short pieces. Uh, but that again, because I've already computed the generating function of all the velocities through the power spectrum, I never have to redo it for the velocities. So what you can show, let's explain a bit more time, is basically at each order you generate the pieces that are compensated out. And so this V, for example, will have a piece at one loop order that has the damping removed. I mean that's how we do it at each order in perturbation. You just kind of do this counting, right? Yeah. Anyways, I mean that's a good question. In fact, it's like it's kind of a neat thing you can do here, but I just didn't have time to. Yeah. Anyways, thanks. Yes. Ah, yes. This is also this is in this case we just did a Gaussian covariance. So probably and I mean almost certainly it's a bit of an underestimation of what the error bars would be. But I at least checked that because in this case for peculiar velocities I mean there really was not a very good way from from publicly available sets of simulations to estimate the covariance. But at least I was able to check from the 25 abacus boxes that we looked that the kind of the disconnected covariance matched pretty well with the covariance estimated from a small number of boxes. It's large, right? So I mean, in fact, the reason that it's powerful in some sense is because the densities and velocities are extremely correlated. So if you go to a scale that's uh, that's 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 uh, that's 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 very that's entirely governed by linear modes, you'll have zero. I mean, you'll have zero decorrelation between these two things. Yeah, one thing I should have said is that we were in fact not able to get the covariance matrix all that's very stable below some small scale. So this fit is done only on scales I think greater than 0.04 megaparsecs per megaparsec. For this reason, that if I try to compute the disconnect covariance, it will not be stable below this scale. But I mean, this is yeah. So this is also a proof of concept because in the real world on large scales there would be decorrelation due to like redshift errors and other nonlinearities. And I really wanted to show that we could recover kind of f of z, f sigma 8 on from fairly nonlinear scales. So I think I mean the covariance estimation is a problem for this, but will not be a problem in real life. In real life, we would use on the other hand, if you didn't use this theory, you would have a problem because of nonlinear. Yeah, I mean it's kind of a complementary thing. That makes sense. Yes. Yeah. No, I mean these surveys are at like no. I mean it's really using the same technology that we use for BAO reconstruction. It's this is just kind of a cute implication of that theory, I would say. And I mean these surveys are at I mean these surveys also usually operate at very low redshifts, so for very small volumes. So you basically I don't think I don't think you really could measure BAO much better from these volumes. I mean what's nice about this is more that it's kind of a confirmation of what we know about the BAO, I would say, right? That it's kind of an unexpected consequence of what we already knew. I mean, in fact, I mean, there's been some proposals in DESI to combine, because at very low redshifts, I mean, DESI is limited by volume, right? And there really is not much room you can grow from galaxy density. So people have asked. I mean, the peculiar velocity working group has made suggestions that you could do some cross correlation with velocities as a way cancel some of the sample variance. But somehow, to me, yeah, I'm not sure how much you could gain from that because we're already very. I mean, the samples at low redshift are characterized by already very low shot noise because they're very densely sampled, and so adding another probe perhaps doesn't help so much. I mean, I wish it would help. Sorry. No, I mean, there are like counter terms as well that yeah that are not shown here, but there are 5 EFT parameters. Even and then there's one more for fingers of God. Yes. Yeah. I mean, but really the statement is that there there are more spectra here than there are EFT parameters, right? So we can individually measure all of them basically. Yeah. Yeah. Exactly. Yeah. You drop some of them when you take the derivative, right? So yeah. So basically, I mean, the statement is that yeah. Yes. Mm. I mean, there are 5, right? So even by the time you've measured the psi one, already have more spectra than counter terms. So by the time you've exited the middle panel, you already have more spectra than you already have equal numbers. So when you measure the auto spectrum of the velocities, at that point you have no degrees of freedom left. Yeah. Yeah. So what people normally measure is they measure this dipole in the middle one, and then the monopole in side two, because those are kind of the easiest to measure and the highest signal to noise. I mean, you can see even actually that the octopole here is fairly low signal to noise, right? But that combination is enough to break the degeneracies. So if you simply measure the monopole, quadrupole, and hexadecapole for the galaxies, and then one each, like the cross power spectrum and the auto, the leading order multipoles, that's enough to break all the degeneracies. Yeah. Yes. Yeah. Exactly. So what this plot is basically showing is that they're consistent, right? So the the most yeah the leading order multiples here are already over constraining them, and then you can see that this octopole and the quadrupole here, they're the lower signal to noise, so their prediction is entirely a consequence of having constrained the other ones. Yeah, so this is really showing the consistency of the EFT for galaxy clustering. Yeah, so in fact, yeah, so adding a single k to the 4 term that only comes from resumming the real velocities, that's significantly improved. So this is what Misha does in class BT, for example, right? Adding that one term, I mean, it improves galaxy clustering, as Misha showed, but also yeah, I mean, you can find here that you can measure that one shape, which is different from the counter term shapes. That one term is enough to improve the chi-squared of all the spectra independently. So I think that's yes, yes. Yeah, and then you can really show if you add in that coefficient, then the error term, the next one scales as k to the 6 mu to the 6, right? So it's really, this is kind of what I was trying to say with this VDG thing, is that if I measure these things either in simulations or data, I can use it to validate whether that model is true, which I haven't done here, but this is one very nice way to look at it, is that there's a consistency implied by these resummations of velocities at any order. So simply looking at velocity statistics would break all these degeneracies, and I suspect you will not find that VDG will the implied resummation will work, but this is just halos. Yeah, this is just halos. So yeah, I mean, so yeah, so the error, yeah, so okay, one thing that's interesting for these peculiar velocity spectra is that, for example, if I look at the velocity autocorrelation, this thing looks like p of k over k squared. And the noise is just some constant shot noise. And the error bars, in fact, are quite large, right? The error bars are like, I think the error bars individual velocities are typically like 20%. But the thing is that because the large scale power goes as P of k over k squared, when you go to low k, even though you have a very large shot noise, it becomes very signal dominated at large scales. So it's, I mean, in real surveys, we would incur an additional such thing. But but I think actually that is not actually such a big problem for doing this kind of inference. For this reason. I mean, this is also why the error bar shrinks so much, is because at large scales you get a very signal dominated sample. Yes. Yeah. Yes. Yes. Hmm. Yeah. No, I mean, I think, yeah, that's, I think, a nice direction to look in the future, but I haven't done it yet. But yeah, as you say, I mean, I can really think of VDG as, I mean, this goes back also to Dennis's question about understanding the small. I can really think of the VDG as separating out this exponential piece for everything, right? So normally, well, then have is that the power spectrum looks like some perturbative part of the power spectrum times this guy e to the I k delta u, but the short part. And so now my power spectrum, for example, is just the power spectrum multiplied by the generating function of the small scale velocities. And if I put this counting parameter in front, then yeah, as Misha says, what VDG kind of assumes is that this guy is a very simple function, right? That this guy is some function of a single, say, a single scaling parameter, and that implies a relationship when you take the derivative of every single velocity. And I think, yeah, I think it'd be kind of nice to check whether that's true, because it could well be that galaxies are very simple in real life, and not in, we shouldn't worry about all these EFT counter terms or HODs or whatever, and it's just a Lorentzian. But yes, but okay, I think that, okay, I can, yeah, I would have I have choice comments about this, but we're I have to make sure I only say true things on camera. Yes. Mm-mm. No, in fact, you cannot in general. You're correct. You're completely correct. But I view this as kind of a complementary thing. So, Emanuele Castorina, who I guess is not here, has done lots of has written a few papers on this, and also kind of relativistic effects. So what I would think that one would do is use these kind of EFT models towards the smaller scales, and then you can add in the kind of line of sight wide angle effects, relativistic effects by by pasting on linear theory predictions, right? Because those, I mean, they become significant in different regimes. So I think the easiest thing to do is to, I mean, also because this estimator that I suggested, well, not suggested, this estimator we've been looking at here, this pairwise thing is not exactly, and this pairwise velocity thing is only really nice in the smaller angle limit. So ideally, what you would do is you would compute the wide angle correction to that, and then add them on. But I think that, well, what I would do is, I mean, those effects taper off faster in K, right? So you have some scales where the wide angle effects are large, and then you have some scales where where the nonlinear effects are large. And so ideally, what you would do is you would paste them together. I mean, this is what people, I think, already kind of do for galaxy clustering, right? No, people haven't really computed like GR effects for galaxies or maybe they have, but it's not very mature that we can do like GR effects for galaxies at very, at at next to leading order or whatever, right? We normally do linear theory plus this. So I think the strategy here would be very much the same. Um, I mean, yeah. One other way you could think about this is that, I mean, the reason people are using, I was showing the kind of the state of the art model people use now is kind of this, and the reason they compute this kind of position space covariance of doing linear theory is because they want to get rid of the line of sight effects. I mean, it's easier to compute this in linear theory than otherwise. But yeah, I think what you would do is you would tape them, is you would taper them together. Yes. Oh. Hmm. Yeah. Yeah. Oh no, no. In the bispectrum, there would be. I mean, there would be more counterterms in the bispectrum. That's right. Yeah, yeah. I mean, but at leading order, for example, there's not a counterterm, right? So here, I mean, it depends on what order you go to, I guess. But also, I mean, to measure this in the I mean, this formula in the bispectrum, this derivative formula becomes more complicated because the bispectrum depends. I mean, this is a statement about pairs of velocities, right? So now you have way more combinations of the velocities when you have three, not three pairs, but you have when I guess you have three pairs when you have three things. Yes. Then yeah, it would be it would be a bit more complicated. I mean, you could do it, but in that case, yeah, in that case, it's kind of not as clear to me that you gain from this simplification that it's just a derivative. Yeah. All right. Oh, all good.